Hello everyone, my name is Cheng. Here is the 15 minutes presentation about deep learning in salt body identification. So the introduction part, basically salt body is very important for reservoir exploration because it can hold the hydrocarbon and also for the drilling strategy because salt is very different from other segments. So we usually need a different drilling strategy. And the seismic data is usually huge, so we try to get automatic way to get the salt body interpretation. And we believe that computer in the region is a way it can help to understand the subsurface structure. And we're using the KIGO dataset, the released by the TGS. So here is the description about the dataset. The image is relatively small, and then it's a 101 by 101 pixel, and there's around 22,000 images in total. So the hardware and software part, we have I'm using the Windows 10 with 16 gigabyte memory, and then we can also try to leverage the GCP, the Google Cloud Computing, to speed up the process. So you can try the A CPUs with 13 gigabyte memory and 100 GPU. And then in terms of the software, we can use, I'm using the TensorFlow 1.11 and Python 3.6 and the OpenCV. So here is the few information regarding how to set up the cloud computing in the GCP. And then you can set up the free trial account with a $300 bonus. And then here how you figure out the configuration with a CPU and 1 GPU. So this is what I mentioned before. And here is how we launch a VM terminal. And then you can just run the script there. So the code example here, we have like breakdown to 7 components with the custom callback is basically to save the weight. And then the data augmentation basically is how to increase the data set. And then the loss function, the matrix, the model, and the prediction. And then we're using the main function to organize everything. So here's what the data look like. So as I mentioned that the image is relatively small, and then associated with every image, there's a mask. So essentially, if it's a black and white, if it's a solid, you use the white color. If not, we use the black color. So here is the evolution of how the geologist is doing the salt interpretation and picking. At the very beginning, we have to do it like by hand. And then later on, industry developed some kind of a semi-automatic way, just set some seed, and then you can figure out the salt boundary. And now our goal is to provide some end-to-end solution. Basically, we provide basically once I have the image, we will try to have the salt body ready. So here is what we use for our matrix. It's using the IOU, so intercept over union. And the reason to use this matrix is put more weight on the boundary, as well as more robust to the imbalanced dataset. And the associated loss function, we usually for binary classification, because we're trying to do an image segmentation, which means that every pixel is either a salt or not. So binary classification, binary cross entropy is kind of the default method. And on top of that, we are using the new loss function called Lambert's loss, which is associated with the IOU. Because IOU, as you know, IOU is a discrete function. This one, in order to use the calculus, we have to extend it to the continuous function. So that's why we extended the function into a Lambert's extension of the Jacobi index. So this is just the basic idea how we do the convolutional neural network. Basically, each layer learns some feature of this image, and then we try to do the interpretation at the very end using the fully connected layer. So when it comes to data augmentation, so basically, I try flip, shift, and then flip plus shift. I also try to do the horizontal flip, but that one doesn't help. I guess that's mainly because of in the real world, if you do the horizontal flip for the subsurface, they might not actually exist because everything is controlled by the physics, constrained by the physics. So I think the first take-home message is that if we do the data augmentation, we have to do it in a meaningful fashion. So if it doesn't exist in the real world, it doesn't make sense to add them into your training process. So, and here is some example for the training set, for the prediction. So I think like here we can see that some of the high frequency change, like right here, is still not able to capture completely, but in general it's pretty good. So, and then in order to make the further improvement, what we try is to try some kind of transfer learning. So Andrew mentioned that actually transfer learning will be the next driver for ML success in 2016. So I think the idea of transfer learning is just like people, human being, once we develop the language, we are able to pass more information, more knowledge to the next generation. So as we can see from here, the learning rate or the knowledge growth trajectory is much higher than without the knowledge. So this one can be viewed as once we leverage the pre-trained model, we're able to get the much better result much faster. And the main model structure is that we're using the UNet. And then for the encoder part, we are replaced by the ResNet 34. And on top of that, we also use some technique like the hyperculant. Essentially, it's like a resize of the put some additional weight on some certain pixel, so that can help to improve the result as well. So for the training part, here is the plot. So for the first row is about the accuracy lost and the IOU matrix, and the second row is about the validation. So we're using the 5-fold validation, and so 4-fold as training, 1-fold as validation. So that's why you can see that the validation plot is more kind of less smooth compared with the training part because there's less data. So here is the IOU score on the testing dataset. So originally on the REST34, and then we also modified REST34 instead, changing the strip equals 1 instead of 2. And then we also modified including the hyperculant and SE squeeze blocks that further improve the results. And then also since the data training data is small, we are using the 5-fold to further reduce the variance. So this is 1-fold, 2-fold, and 5-fold. And we also try some random noise, but it doesn't seem it's helping in 1-fold as well. So in the end, we try to see how can we do the quality control, because we have like 22,000 images. The image is very small, 101 by 101. So it's challenging to go through them one by one. So we try to figure out a way whether we can combine them together. And the idea is coming from the continental drifting theory. So at the end of the day, all the continental can be combined together into one piece. So there's available algorithm online, Drossel puzzle machine learning method. So here's the detailed step for how to do this jigsaw puzzle method. So essentially, it's try to compare the similarity between two images on the boundary, and then they have many other options like up and down, down up. So all the other options and can be done using the KNN approach, and then so we're able to leverage this method to combine all the pieces together. So this is actually what it looks like. So you can see that it's much easier to do the quality control, and then once we normalize the boundary stuff, we don't see the boundary effect. It's like a whole picture. Yeah. So here is our conclusion. So the key way to improve it. So data augmentation, though, for sure we need more data, but you have to have a physical meaning. So for example, if you do the horizontal, if you do the vertical flipping, it doesn't help because it doesn't represent the real situation. And then the model architecture is like a reverse engineering approach. So basically, try different method and then see which way is helping. And then when the result get improved, we try to justify that. And then ensemble approach, meaning that we have like use the multiple folds to further reduce the variance. And then in the very end is that how to leverage domain knowledge. So we kind of have hypothesis that if actually we can combine them, those small image into one big picture, and then we justify that. So now it's much easier to have the together. So yeah, thank you very much.